Hello everyone, we're going to talk some more about reduction now, and hopefully you already have some basic idea about what a reduction is because we talked about it in the previous lecture. So if you're still not okay with that, please go watch it again because we're going to go deeper. So you're only going to get more confused if you still have no idea what a reduction is. And let's not forget about the big picture. I need you to understand this diagram. I need you to understand the different complexity classes by now. I need you to understand what NP-complete is, what NP-hard, what NP is as well. And there's not that many definitions, right? We know that NP-complete means it's both NP-hard and NP. So NP-hard means that any problem in NP can be reduced to it. See that word again, reduction. And also NP means that you can verify the solution in polynomial time. So, look, you need to know all this stuff before we can move on, right? So if you need to go watch the previous lecture again, go do it. Like, wait until you really understand everything before you start with this video. And this is probably the last hard theoretical stuff that you have to do. There's only one more topic after this one, like a small one. It's called approximation algorithm. Conceptually, that is easy. So the way I see it, this is it. This is the big one. So again, make sure you understand all the prerequisites before you go into this video. Okay, so reduction is about converting one problem into another problem. It is exactly like I said here. You have two problems, A and B. You can convert from problem A to problem B, and you can solve problem B. So there are two reasons why you want to do a reduction. The first one we already talked about, and it's kind of obvious. You want to solve A using B. The second one is actually the more important one, and we're going to spend a bit more time on that. You use reduction to argue that B is as hard as A. And this may sound strange to you for now, but really this is the main reason why we are studying NP problems. Look, we talk about using B to solve A. We talk about the first point. So you have an NP problem, you can reduce it to a polynomial time problem, and you solve it in polynomial time. You're happy because you have proven that P is equal to NP. But that's not what we plan to do in this unit. And I don't know about you, but I don't plan to do this with my life either, because I don't think it can be done. I think P is not equal to NP. So we are talking about NP problems in this unit because we want to do number 2. And again, you may think that this is weird. Why are we doing this? Why are we trying to argue that B is as hard as A? Well, if you find this is strange, that's why we're here, to make sure that you understand why. So we're going to talk about them both again. But the goal is always going to be the second point, that I can argue that B is as hard as A. Now, with reduction, this is the image in my head. I got an input for A, I changed that into an input for B using this thing called the reducer. Then I solve it using the algorithm for B, this solver thing here. I get some sort of solution in B, and all I have to do is convert it back to A. Is this exactly how you do it? Maybe not, but this picture is kind of clear to me. And conceptually, it is easy to understand. So I think reduction is easy to understand. I know I keep on repeating it so that you may start thinking that it's actually more than what it is, but it really is not, at least not in this unit. Now, there can be a bit of subtlety here. For example, like reducer, do they work in both ways? And also with the decision problems. Well, if your problem here you only need yes or no as the solution to your problem, then if I can reduce problem A to problem B and I can plug it into the solver, it's only going to give me yes or no anyway. So why do I need to send it back to A? Like why do I need to do the round trip back to A? So it really is quite simple. Although if you are doing complexity theory properly, then you have to be really careful with how you define reduction. As I mentioned before, we're skipping a lot of this stuff. You have to deal with things like languages and strings. You can see this happening in CLRS, but again, we're not doing all that. We're skipping the hard theoretical stuff. All I want you to care about is the 2 points I mentioned earlier, particularly the second one, but we'll start with the first point, and that is if I can reduce A to B, then I can use B to solve A. And we care about this because we know that there is a class called NP-complete. And every problem in NP can be reduced down to problems in NP-complete. So just get one problem done in P, and you prove that P is NP. Just one problem in NP complete that you can do problem in time. You're done. But one more time, that's not our goal. That's too hard. But let's talk about it somewhere anyway. Because you might think, I'm just reducing an NP complete problem into a problem in time problem. That's all I have to do. Why is that so hard? Well, here's an example. Traveling salesman. By this time, I hope you know what traveling salesman is, so I'm not going to say it again. Well, I describe it here anyway. Remember, it's the decision problem, so you're just asking if there's a route of length at most L or at least L. Doesn't matter. What matters is it is a yes or no question. So why not just get all the possible cycles, put them inside an array, and hey, all I need to do is go to the array and find the one with the least distance. That's a linear search problem. Galaxy brain time. Well, no. Because making that array with all the possible cycles, well, you're gonna need exponential time to do that anyway. You're solving the problem in exponential time if you do that, right? This is not something that you do. As in, if you got an NP problem and you reduce it down to a polynomial time algorithm, but the reduction is exponential, that means you need an exponential time to do it. It's an exponential time algorithm, which is useless because you want to have a polynomial time algorithm to do it. The reduction is part of the algorithm, so it must be polynomial as well. Same thing with the conversion from any problem NP into an NP complete problem. We must do this in polynomial time because otherwise there's no point. The goal is to do things in polynomial time at all times. So that was actually in the definition for NP-hard earlier as well, by the way, that a problem is NP-hard if every problem in L can be reduced in polynomial time. So the thing is, you can do a chain reduction, as in you reduce a problem many times. You go from problem A to problem B to problem C to problem D, and if they all take polynomial time, then the combination of all these reduction is still polynomial time. Even when we're using the decision version of the algorithm to solve the optimization version, you remember that this is a polynomial time conversion, right? Because if I can do the decision problem in polynomial time, like we did traveling salesman here, then all I have to do is do it k times. So keep everything in polynomial time. That really is all I want to say on the first point. So really, when we say you want to use B to solve A, you know what this means. All I'm adding here is that everything must be done in polynomial time, otherwise it's pointless. And we can now move on to point 2, which is the more important one. Point 2 is, I can argue that B is as hard as A. You may find this hard to believe, but this is the main point, at least for us anyway. Reduction is a way for us to say that a problem is hard. Let me say that again. Reduction is a way for us to say that a problem is hard. Let me say that one more time. Reduction is a way for us to say that a problem is hard. That's really why we do reduction. Because you want to go to your boss and say, the problem you told me to do is hard, and I can prove it. I have a lot of famous people behind me. They all say it is hard, so it must be hard. This is why you're doing reduction. Okay? So we're going to need some notation now to make the explanation easier. If problem A can be reduced to problem B, we write A less than or equal with this little p b. I don't know how to say this symbol. Less than p, I don't know. Anyway, when I first saw this notation, I thought this is B reduced to A because, you know, this kind of looks like an arrow and the arrows kind of go to the left, so B goes to A. But no, this is a less than or equal to symbol with a little p there to signify polynomial time. And the reduction is actually from A to B. So don't look at it like an arrowhead. It's A, this symbol B. I don't know what to call it, but it doesn't matter. This means A can be reduced to B in polynomial time. So if A can be reduced to B in polynomial time, which one do you think is harder? My favorite story for this is again the Com 125 student who used sorting to perform mob find max. I hope you remember that story from the previous lecture. I can use sorting algorithm to find the maximum in an array, but to sort using find max, I have to muck around a bit. I have to do extra stuff, and I have to call find max many times, maybe, right? So sorting is harder, or at least it is as hard as find maximum. And this is where the notation kind of makes sense, because in terms of difficulty, B is as hard as A. As in B cannot be less than A. B cannot be easier. Now, there's a formal proof for this, which we are avoiding because, again, a lot of languages, strings, all that stuff. But I hope it's intuitive anyway, because we are actually saying that if you can solve B, you can solve A. So B must be harder. Because if you look at the opposite, if you can solve A, can you solve B? The answer is maybe not. Like, think about sorting and find max again. They can be of the same difficulty, so maybe you can. But surely B cannot be easier than A. So this notation kind of makes sense. Now, just to make sure that you understand all this about which one is harder, let's look at all the possibilities. You can kind of think that easy is P and hard is NP or EXP. And what we're asking is, can I reduce A to B? All right, first case, A is easy, B is hard. Can you solve an easy problem in a hard way? Yes. Think about that poor Common Voice 5 student again with the sorting and find max. He's pretty famous now. And this guy's really helping you understand this unit. So I can do something easy in a hard way. I can convert linear search into traffic salesman and then solve traffic salesman to find the solution to the linear search. And why on earth would I do that? I won't, right? But still, it can be done. Now, so that is fine. Now, second case. A is hard and B is easy. You shouldn't be able to do this. That's like trying to do traffic salesman using linear search. If something is hard, then it is hard. You can't do something hard in an easy way. In fact, if you think that something is hard, but you can actually do it in an easy way. For example, if you think A is hard, but you can convert A to B, and then B is easy, that actually means that A is easy, right? And the last one here, it's not interesting because hard stays hard. Yeah, meh. Actually, these last two, they're not interesting because if you just stay in the complexity class, P is still P, NP is still NP, or EXP is still EXP. So again, not that interesting. But anyway, these are all the possibilities that you can have. So how are we going to use this? Now, this is what I mentioned earlier. If you can reduce A to B and B is easy, what does this mean? It means that A is easy as well. And this is what we can use to prove that B is NP. By reducing something which is NP complete to a polynomial time problem, we have shown that every NP problem can be done in polynomial time. You prove that P is equal to NP. Again, that's not our main point though. I hope you're fine with this. It's a great idea. If it can be done, great. But our main point is the last one here. If A is hard, then B is hard. I'm going to ask the question the other way around now. See, before I was asking, if B is easy, what about A? Now I'm going to ask, if A is hard, then what about B? If A is hard, then B cannot be easy. All right, for now, you think about NP-complete problems being hard, right? So if A is an NP-complete, and I can reduce A to B in polynomial time, then B must be, what do you think? You may say, oh, B must also be NP complete. Well, actually, B must be NP hard. Remember, the definition of NP hard is that any problem in NP can be reduced down to that problem. So A is NP complete, so A is NP hard. So I can reduce any problem in NP to A. Now I can reduce A to B, so I can reduce any problem in NP to B. That makes B NP hard. Whether or not B is NP complete, well, can you verify the solution in polynomial time? If you can, then B is NP complete. If it's not, then it's just NP hard. So you see now how I need you to be okay with the definitions, because we're just going to use it like this. So yeah, hopefully all that makes sense. And we're almost done. We're almost done. Because this is it. The point of doing reduction is not to ask if B or A is NP. That's too hard. We use reduction to show that B is NP hard by using an NP hard problem for A. So here's the scenario. You got B. You don't know if it's hard or not, right? So you pick up problem A, and we know that A is NP complete. You reduce A to B. What you have done here is that you have shown that B is also NP hard. Now, if you can show that B is NP, that we know B is NP complete, but that's not important. Like, the important stuff here is showing that B is NP hard. You have shown that your problem is hard by using another hard problem. Always remember the direction of the reduction. You are reducing from a problem that you know, A, this will be NP complete, to a problem that you don't know, B. and you want to show that B is NP-hard. This is it. This is the main point. You understand this, you understand the most important concept that you need to understand, right? I'm going to talk some more about like maybe historical stuff, and we're going to be doing reduction later on. But if you don't understand what you're doing, you don't understand why you're doing something, then you're not going to appreciate it. So make sure you get everything up to this point. All right. Now, what you might be thinking is, if I want to show that something is NP-complete, then I need something else which is also NP-complete, right? Because if I don't know if B is NP-complete or not, I have to find A which is NP-complete and then reduce it to B. It's almost like you transfer this property from problem to problem. So the question is, there must be an original problem, right? There must be the first NP-complete problem. So what is it? Well, this is the famous Cook-Levins theorem, which actually establishes the first NP-complete problem that we know. And the problem is the Boolean satisfiability problem, or the circuit satisfiability. What is circuit satisfiability? Well, you got a bunch of circuits here. You have the NOT gate, the AND gate, and the OR gate. Well, you know what these operations are, right? So with the OR gate, if X and Y are both 0, then it's going to come up with 0 as well. If X and Y, well, one of them is 1, or both of them are 1, then you're going to get a 1. So if I build a circuit based on these gates, right, and start off with x1, x2, and x3 here, the question is there a combination of x1, x2, and 3, and 1s and 0s, such that I will end up with a 1? So the picture on the left here, yes, there is. You can trace it. You can trace the workings here. The one on the right, there is none. You can give it a try, but you will not be able to come up with a 1 here. No matter what x1 or x2 or x3 that you choose, there's no combination that will give you 1. You probably have seen this version instead in COM 225, like the very final week. This is called SAT problem. That's the Boolean satisfiability. And this one has a trivial solution. You just set everything to 1. Well, this is probably the one that you've seen, right? And they're kind of the same thing. You can modify one problem into the other, although I think the circuit version is the first one. They prove that it's NP-complete, and then they reduce it down to this version here, which we're just going to call SAT problem. Now, the proof is beyond the scope of this course. Like, when you read CLRS, and they say that the proof is beyond the scope of this book, this is CLRS we're talking about, well, we're not going to be touching that proof, all right? We're going to stay away from it. But what it says is that SAT, either version, is the mother problem, as in it is the first NP-complete problem that spawns other NP-complete problems. Well, it's not like you give birth to these other problems. Like the problem's already there. You just show that they're NP-complete. It's like you got people and they became vampires or something. That's how I see it. Anyway, this is the roadmap of the reduction that can be done. This is how you show that all these guys are NP-complete. Now, we're not going to be doing any reduction now, not in this video. May do that in the next video. And we're definitely not going to do all of them. Actually, we've done one. You saw how we can reduce Hamiltonian cycle to reference Salesman in the previous lecture. And doing reducing SAT to 3-SAT is almost like a rite of passage. Like every computer science student, they have to go through the proof of that that 3-SAT is NP-complete by reducing SAT to it. This was done in COM 225. It's pretty easy, pretty boring. Anyway, you should try to know all these problems, because you may have to reduce them to your problem one day. That really is a goal, for you to be able to recognize that the problems you have to solve is hard. Really, that's the whole point of learning P versus NP, in my opinion, for you in this unit. Okay, so that should sum it up. Key point number 1, the reduction must be done in polynomial time. If it's not in polynomial time, then it's kind of useless. This is the notation for reduction. We can reduce A to B if we know that A is NP-complete, and B is in P, then we have proven that B is equal to NP, because we can reduce every problem in NP into a polynomial time algorithm. But again, this is not what we're doing. This is not what we care about. What we care about is the second point here. we have a problem B and you don't know anything about B. You have another problem A, you can reduce A to B, sorry, A is NP complete, and you can reduce A to B, then B must be NP hard. Or if B is also NP, then B is NP complete. So make sure you understand the direction of the reduction. Make sure you don't mess it up. Are we going to be doing any reduction? You bet we will. At least in the workshop, we'll do some reductions because you need to know how to do reductions. But really, this is just converting one problem into another problem. And I will definitely ask you to do a reduction in the exam or in the test. So yeah, probably gonna make another video that shows you reductions. We kind of see one already in the previous lecture. So we'll do more in the workshop. You go have some practice and you'll be fine. It's actually not that hard most of the time. Well, at least the ones you gotta be doing, other things gotta be hard. Okay, so that's it for this one. Like I said, there's only one more topic, which is conceptually new, and that's approximation algorithm, and I don't think that's actually hard to understand. That one is more about doing, like it'd be more practical. You gotta do. Whereas the last few topics, like the whole NP stuff, reduction, is theoretical. So I think it's harder. And so I think we pretty much close to finish now. So maybe only 1 or 2 more hours of lectures and then we're done with this unit. So great, you got this far. And I'll see you in the next lecture.